Hello everyone, welcome to the webinar today where we're going to be going through our CFD software called inFlux. During the webinar, if you have any questions, please go ahead and ask them via the GoToWebinar interface. We do have about 10 to 15 minutes for questions at the end, and if we don't have time for all of them, we will follow up later via email. If you would like to listen to the webinar again at a later date, we'll have the recording available on our website and YouTube channel. In our previous webinars, we have mainly focused on fire and gas mapping, either with Detect 3D or using risk-based approaches. But today we're going to talk only about CFD and what can be done with inFlux. A little bit about me before we start. My name is Oliver Haynes. I'm the co-founder of inSight Numerics and the lead developer of both Detect 3D and inFlux CFD software. I started my career in technical safety consulting, where I mainly focused on CFD projects, but my real interest developed during that time was in writing CFD codes. I'm interested in really pushing the boundaries of what CFD can do, especially in the field of oil and gas safety. Before oil and gas, I got my PhD in CFD from the University of Manchester in the UK, and my master's in aerospace engineering, also from the University of Manchester. In 2013, I started inSight Numerics with Alan Miller. As a company, we devote 100% of our time to developing software and supporting our customers' projects. We don't do any consulting work ourselves as a matter of principle because we don't want to compete with our customers, and we think our goals are better aligned with our customers by just supplying software. As well as inFlux, which is the topic of today's webinar, we are perhaps better known for Detect 3D, which is very popular software for fire and gas mapping, but in fact both software products are themselves very widely used. We supply software to all types of companies, right from the very largest oil majors to many engineering firms, and from the largest consultancies right down to small one-man band operations. So our goals today are to introduce you to inFlux and its capabilities and show you how you can run CFD projects with inFlux. We'll particularly be focusing on how you can be more productive on projects that require CFD, what type of projects inFlux can be used for, and how inFlux is different from other CFD codes. Before we get to the rest of the webinar, I want to invite you to take a quick poll so we can see the level of knowledge of CFD in the audience. So I'm just going to launch a quick poll. So if you could respond to the poll. Once we understand this, it makes it easier to the rest of the webinar and the software demo. Once we know the audience, just give it a few more seconds. We've still got some responses coming in. Okay, I think we've got almost all the votes now, so we'll just review those poll results, and we can see that the majority of people on the call are new to CFD, and the next group is most popular is that they've reviewed CFD project work but not done any themselves. And the minority of people on the call have done some CFD projects themselves, which is great. We can tune the rest of the webinar to that type of audience. I do think, even if you're sort of new to CFD, you've probably heard of many CFD codes in the industry during the course of your career. And you might be wondering why we need another CFD code. So I thought I'd give you a quick background to the origins of inFlux and why it exists in the first place. Actually, the first ideas about writing a new CFD code came from my consulting days as a CFD engineer. And when I stepped back from project work and took a broad perspective of the work I had done, a few things stood out to me quite clearly. The first was that a number of tasks that I did on projects could be automated. Many projects I did were very similar, and I did them in the same way, meaning that I was essentially part of a manual algorithm. I was optimizing using my own work as part of the algorithm. This was kind of useful to me because it meant that I could be very efficient as a consultant with my project work. But then again, after a time when you do the same thing over and over and over again, that could be automated, it didn't seem like a productive use of time. It felt more like I was handling, operating the handle of a machine rather than providing real value from my own expertise. The second thing I noticed was that how much of this manual automation was being done either to fix problems in existing CFD software or to extend their capability in ways that were really the responsibility of the developer of the software. Even in projects that were the primary use case of the software. These weren't edge cases, they were what the software was designed for, and yet we still needed to extend them. So instead of actually applying my own CFD knowledge to projects, I was instead spending my time trying to maintain custom scripts that other people had written, or writing other scripts to do quite mundane tasks like getting boxes to match up with grid lines. And it just seemed an absurd waste of time. I didn't get involved in the industry or involved with CFD to do this type of mundane work. And I knew others were in the same boat too. In fact, it seemed to me that the CFD software that was commonly used in the industry led to a sort of industry-wide inefficiency. We've got lots of talented engineers out there, but a lot of the time is spent creating workarounds for deficiencies in CFD software. And it's not just a personal frustration either. There's a significant project cost associated with this inefficiency. So I knew that this had to change. inFlux was really born out of a desire to make our whole industry more productive and to use CFD in a simpler and more convenient way. I really wanted to remove all the complexity, the unnecessary complexity and cost of CFD and promote consistency in results. I felt that a new product had to increase the effectiveness of engineers, not bog them down writing scripts, but actually increase their effectiveness and productivity. I also felt that it had to be flexible to project requirements. It's very easy to imagine software running from start to finish, but in practice, it runs from start to somewhere in the middle, and then the project changes and you have to go back and redo things, and you have to build in that flexibility to software. The next thing I was very keen on was making CFD software accessible to all engineers, not just CFD experts. It again was very apparent to me that on projects you had engineers that knew about the project. And when they needed to do CFD, they needed to use a CFD expert. And that line of communication sometimes didn't work very well. The CFD expert heard one thing, whereas the project engineer meant another thing. And when the results came back from the CFD, often the project engineer couldn't understand them or didn't know how they applied to the problem they'd just given the CFD expert. So there was this disconnect that I felt was quite unnecessary. Again, level of inefficiency in our industry. And the final property of new CFD software was that it has to be consistent, meaning that all users get the same results. This is a key property of inFlux that is not necessarily a property of other CFD software. There's been many interesting studies out there that show even when you give two CFD engineers the same project with the same software, they'll get different results. And that's certainly true in our industry, certainly true, because there's so many personal decisions that you make along the way based on your experience, and all of our experience is different, so we end up with getting different results. And that's not really a desirable situation to have. So we've built inFlux to be consistent among users. And so really these were the principles on which inFlux was created. We started work on it in 2015, 2016, and we released it in 2018, almost 3 years ago to the day. We continue to develop it. It's very much ongoing development, but already being used on many projects all around the world. So let's start with the very basics. What is inFlux? So at the most basic and simplest definition, inFlux is CFD software. And I say that to place the software in the same category as CFD software like Flux, KFX, CFX, Fluent, StarCCM, OpenFOAM, software like that. In other words, you can use inFlux to solve CFD simulations. However, I would slightly modify that definition and say that inFlux is software for CFD projects. And to explain what I mean by that, I think it's worth looking at what traditional CFD software, how that works. A very basic model is that traditional CFD software is concerned primarily with solving one CFD simulation. You can extend it out to solve a few CFD simulations, but projects in our industry typically have hundreds of simulations. And so to start solving all of them, you have to start writing your own scripts to link together results from each simulation and to set up those simulations. And this whole process is time-consuming and messy. There are some companies out there that have been working on CFD for well over a decade now, and some of their user scripts are a decade old, and they've been written by several people, and there are many versions in different folders or network drives, and it's very messy, the situation that we're in now with this type of approach to doing large CFD projects. So inFlux, by contrast, contains the whole CFD project. Its user interface has been designed to handle thousands of CFD simulations. So there's no need for any external scripting because it's all there in the software. So it is a much cleaner and more efficient workflow. There's no external code scripts to maintain. But I hope you will see at the end of the webinar that actually the simplicity extends further than just being able to handle CFD projects, but it in fact gives anyone the ability to use CFD without necessarily being a CFD expert. So for example, let's say you wanted to do a quick kind of hand calculation and you wanted to use Excel to do it. So this is a very common thing that we as engineers will do. We don't think for one moment of outsourcing that calculation to an Excel expert and then waiting on the results. We don't do that because we know we can do it ourselves, and it's so much slower to outsource it to an Excel expert. And we also wouldn't know whether, although that person's an expert in Excel, whether they can actually do our calculation for us is another matter. So we do it ourselves. inFlux is the same, but for CFD. So if you wanted to run a CFD simulation yourself, you don't go to necessarily to a CFD expert and wait on the results. You can actually run it yourself. Something that our inFlux customers do is to run very quick design iterations with inFlux. So they might have a project meeting in the morning where they discuss different design options, and they have the results then in the afternoon. Another example, a story from one of our customers, is that they actually run inFlux during meetings. So while the meeting is happening, they'll look at different designs with inFlux, and they'll get the results during the meeting. It's a completely different way of working with CFD when you can use it that flexibly. And I do want to mention in this slide that all of this is underpinned with validation. We've had lots of industry participation with big players sharing data from large-scale experiments and other types of experiments with us to help with validation. And that's all summarized in our validation guide, which is available on our website. So how does inFlux achieve all these things? The first thing that is different about inFlux than other CFD software is its level of automation. inFlux is highly automated. We automate all the typical tasks of running a CFD simulation, such as sizing the domain, meshing, setting up the model and making the numerical choices, and post-processing. And this isn't necessary because if you have a project with 1,000 simulations, you simply don't have time to handle each simulation individually. So it has to have this high level of automation. The second thing that marks inFlux out as different is that it's very fast. Typical run times for ventilation simulations are in the range of 2 to 10 minutes, and for a dispersion simulation, 5 to 45 minutes. It's very rare that you get a simulation that's an hour or more. In addition to the run times, it's very fast to set up simulations. You can have a project with 1,000 simulations going in a few seconds. It really is that fast to get everything up and running. It achieves this level of speed due to using a very highly efficient mesh that is, while being more refined than meshes typically used in our industry, actually uses fewer cells. We make sure that every single cell is working hard. There's no slackers in the inFlux mesh. The third thing is that inFlux is accessible. Because it's very easy to use, you don't need any CFD education, and about half of our users currently of inFlux don't have any background at all in CFD. They've never run a CFD simulation before, and these are people running projects that have several thousand CFD simulations in them. They're not small projects, they're huge projects. It also didn't, as I mentioned, require any scripting, so you don't need to know additional programming languages to get things running on certain computers. But the cost of all this is that inFlux is slightly narrower in scope. than other CFD software. It cannot be used on all types of projects. So the types of projects it can be used on are things like ventilation and wind chill analysis, where you can look at air changes per hour. You can do that indoor or outdoor ventilation. You can also look at helideck turbulence. It has an advanced turbulence model in there for looking at vertical velocity fluctuations above a helideck. Very common use case of inFlux is just for dispersion modeling. So looking at thermal plumes or toxic plumes, accidental leaks, blowdown, and then it can also then be extended to risk-based analysis. So you can look at risk-based gas mapping, which we've covered in a previous webinar, or some of our customers use inFlux as for the dispersion modeling portion of an explosion project. So you can't yet do explosion modeling with inFlux, but you can do all the dispersion modeling to support your probabilistic gas cloud sizing. So we're going to look at a demonstration now of inFlux, and we can't show all of the capabilities of inFlux in a short demonstration. So we're going to look at a few simulations, and we're going to just look at some dispersion modeling. But hopefully you can see the principles of how it works to apply to other types of CFD projects. So the user interface of inFlux is very similar to that of Detect 3D. If you've used Detect 3D before, you'll have a very easy time learning inFlux because it's exactly the same layouts of the user interface. You can also import files from Detect 3D. So if you've done a fire and gas mapping project, you can import that Detect 3D file into inFlux and start running CFD on it. In terms of CAD, it has the same geometry importer as Detect 3D. So you can load in various file types. The most common are the DGN files and DWF files. So DWF is exportable from Navisworks. So if you have a file in Navisworks, you can get it into inFlux. Also supports various other CAD formats, including KFX and Flux files, so you can import those as well. In this example, we're just going to import standard geometry that we use for demos. It's relatively simple geometry, but it's still quite complex from a CFD point of view. So what we're going to do is to run some wind simulations on this site and then look at some leaks from this kind of region and see how the gas cloud develops and what we can do monitoring the gas cloud with inFlux. So I'm going to run a wind simulation first. It's very easy to do that. You just select your wind speed and wind direction. I've got here by default 5 meters per second from the north, so I'm just going to add that to the project. So already the simulation is running. You can see the progress here. So it did a number of tasks that typically a CFD engineer would do. And the first one is that it decided how big the domain has to be. This is where it's solving the equations of CFD. And it takes a view of how big the CAD file is, how densely populated it is, the congestion in the CAD file, and then it takes a view of how big the domain needs to be to properly solve the equations. The next thing it did was to generate a mesh. Again, this is automated. So it refines the mesh closer to the ground as the cells get closer to the ground, the mesh gets more and more refined. But it also refines the mesh near the CAD. You can kind of get a sense for that here. It refines the mesh not only around the actual objects in the CAD file, but also in response to the gradients that are generated by the CFD. So high velocity gradients cause the mesh to refine even more. So you end up with a very high quality mesh without any user input. You can see that I didn't tell it to do anything with the mesh, it was all automated. And the result is that the simulation is now complete, and we can start looking at the results immediately from this simulation. So these are just the velocity vectors at a certain height. You can see, for example, how the vectors show the wind changing direction locally in response to the geometry in the file. You can see the vectors going around the tanks, and you can see things like recirculation regions behind the tanks. So it's calculating the full 3D flow field, and we can drive that point home by moving the vectors up and down. So you can see the vectors change with height, and the vectors kind of going over the two tanks as well as we move them up higher. So next we want to look at a leak, an accidental leak. So we're going to add a high pressure leak source to the project. Now there's various types of leak source you can add in inFlux. We've got the high pressure leak that we're going to show you today. You can also add features on that leak like depressurization, isolation, blowdown, etc. But you can also add low pressure leaks like a thermal plume from a stack or an evaporating pool, for example, as well as adding things like HVAC, inlets and outlets and through flow fans. It's quite flexible with what you can add to model gas in the domain. But we're just going to add quite a simple high pressure gas leak. We're going to use a single component gas in this case for simplicity, but you can create multi-component gases too and use them as the basis of your leak. So I'm just going to pick out where I want the leak to be from. And I can then set properties of the leak like the upstream pressure and temperature, hole size, things like that. These are not CFD parameters. They're parameters that you would know working on your project, what the kind of scenario that you want to model. So I can just add that to the project. Now to model this leak in that wind, I have to set up a dispersion simulation that combines the wind that I just modeled with the leak that I just added, and just press add item to add that to the project. So again, it's doing a lot of things now in the background to run this CFD simulation. Notice that I did very little to set that up. I'm just adding parameters that I would know about a leak and the wind's speed and direction, and then we've got the dispersion simulation running. So in the background, it's again set the domain. The domain is the same size as the wind simulation, and it can automatically resize itself during the simulation as well if it needs to. next is that it created the mesh, and we can see the mesh here. I'm actually going to show a plan view of the mesh. And what you can see is the refinement of the mesh, again, around the geometry, but also around the leak. And if we zoom in to the leak, you can see that it has a very highly refined mesh around the leak source. If we click on the mass fraction equation, this is the CFD equations running in the dispersion simulation. These are intermediate solutions. You can kind of see the leak source coming out. And if you just take focus on the mesh now, you'll see it automatically update. So the mesh changed. You may have seen the mesh change. What's going on there is that the mesh is refining itself around the gas cloud. So it's running the simulation to get a kind of intermediate solution about what the gas cloud is going to look like, and then refining the mesh around that gas cloud and then rerunning the simulation. It's actually doing this again now. So you just saw the mesh change again. Now this is really useful because it's kind of deciding itself how refined to create the mesh without any user input. It also means that you get a very refined mesh around the gas cloud in a very efficient way. If you think of the kind of CAD files that we use in our industry, they're normally very large, large oil platforms or FPSOs or something. We might have a small 10mm leak that we want to look at. Well, with inFlux, the mesh only refines itself quite local to that leak source and doesn't bother refining mesh cells 300 meters away that really have very little impact on the actual gas cloud. So you can kind of see already that the mesh is, you can kind of get a sense of where the gas cloud is going really just by looking at the mesh. But this is really only for kind of academic purposes. We don't need to think about the mesh or look at it. I'm just really showing it as a point of interest. Many of our customers run inFlux simulations without ever looking at the mesh or knowing about it. It's all handled automatically. So I mentioned that the typical traditional model of CFD is to have one simulation running in the one user interface. And I want to show how inFlux is different by looking at many simulations, several hundred now are set up in the user interface. So I can add more wind conditions by selecting the wind speed, but then looking at different wind directions. So I'm going to select all the wind directions I haven't looked at and add those to the project. I'm then going to look at different wind speeds, let's say 10 meters per second for all wind directions, and let's say 2 meters per second at all wind directions as well. And now I have 24 ventilation simulations added to the project. Now these are all automatically lined up, ready to be run one after the other. If you see the scheduler up here, it shows the list of simulations of what's running next. At the moment it's running my dispersion simulation, but next it's going to run some of the ventilation simulations. Now I've only looked at one leak, of course, and in a typical project you'd want to look at multiple leaks. So you can keep the process conditions the same, but just start clicking on different parts of the CAD file to add more and more leaks to the project. It's kind of very simple to do this. You don't have to have leaks that are aligned with any axes, for example, you can here, for example, have leaks at 45 degrees. You can also have leaks kind of going upwards at an angle like this, really any direction that you want. And then once you've added the leaks that you want to look at, you can create a set of dispersion simulations for all of your wind conditions just by selecting all of them, and then selecting all of the leaks that you just added and selecting add item to the project. And that's just added an additional 216 dispersion simulations now to my project. So you can see them down here. Now, in fact, this number of simulations is quite small for an inFlux project. Typically, our customers run projects in the range of 1 to 10,000 simulations in one project. So a few hundred is in fact very small. The dispersion simulation we ran has now complete, and we can take a look at the results from that simulation. So I can look at, for example, the flammable gas cloud. Now I can look at contours of concentration as well, a kind of standard plot of that. But I'm actually going to look at the ISO surfaces, so the 3D clouds. Now you can plot ISO surfaces of any variable. Here you've got multiple variables to pick from. I'm just choosing the flammable gas volume fraction. And you can see this flammable gas cloud here. So this is the 100% LFL gas cloud. You can see the leak coming out and expanding from the leak source and then impacting the vessel here. You can also see the impact of this sort of pipe work. So the mesh is smart enough to pick up that pipe work as being an important factor and will refine the mesh around that pipe work to properly evaluate its impact on the gas cloud. Now, we can then look at, say, lower gas concentrations. Let's say 10% LFL. Now, what you'll see with this gas cloud is that because we're looking at a lower concentration, what happens is that the gas cloud impacts that vessel and loses a lot of its momentum and then gets turned around into the wind. You'll see, for example, that the vectors that we looked at before are flowing from right to left. So the leak opposes the wind direction, and the gas cloud then starts flowing with the wind through the domain. And then if we look at a very low concentration, like a 1% LFL, we can see in this case the gas cloud is much larger because it's a lower concentration, and you can see it again flow through the domain. But you can also see the gas being pulled back towards the tanks, which is kind of interesting. And again, if you look at the vectors, it's due to this flow reversal behind the tanks. So this kind of level of detail is kind of available to you from the CFD simulation. I mean, if you were given that wind direction and leak direction and leak location, you may not predict gas concentrations at this point here behind the tanks. So it's kind of useful to have that level of detail available to you in the CFD model. Now, as well as looking at visuals, we can also look at monitors. So let's say I wanted to know what gas concentration was just above this walkway here. What I can do is to add a monitor point, add it to the walkway, and then increase it by a couple of meters. So we've got a monitor point now. That will tell me everything about the flow at that particular point. As well as monitor points, I can also add monitor lines. A monitor line tells you information along the line, so it could be anything like the maximum or minimum value of a variable or its integrated value. So you might put this around the perimeter of a site to evaluate what the maximum gas concentration is leaving the site, or you could use it like an open path gas detector where you can integrate the gas concentration to get the response for the open path gas detector. Also, you can look at monitor regions. So I can quickly make a box around my leak. And that's going to tell me volumetric data. So how big the gas cloud is. And we'll quickly take a look at this monitor data. Now, I have to, because I added the monitors after the simulations were complete, it's now just going back to those simulations and acquiring that data for that monitor point. So we can see that we've got now 5 simulations complete in the project. The ventilation simulations are running in the background while we're doing all this. But I might want to look at flammable gas volume fraction at that monitor point I added. And I can see it's 2.1% LFL. So this kind of makes sense because it's within the 1% LFL gas cloud, but it's outside of the 10% LFL gas cloud. So a value of 2% LFL aligns with what we're seeing here with the isosurfaces. Now if we focus on the monitor line, we can look at various variables along the monitor line. If we had a multi-component gas, we'd be able to look at each component individually. But for example, we can see the maximum value of LFL, so 20% LFL. We can look at an integrated value. So this is a kind of signal from an open path gas detector, so it's 1.8 LFL meters from the gas detector, if that was an open path gas detector. And finally, the gas cloud. This is for the dispersion simulation and looks at volumes. So you've got LFL to 100%, LFL to UFL, the equivalent stoichiometric volumes of both Q9 volume and then the mass of the flammable mass as well. You can create custom gas clouds too. So you can say, what is the volume between 20 and 50% LFL, for example, or really any variable you want. And that's also all exportable to Excel. All of this monitor data is exportable to Excel. So I hope I've kind of demonstrated to you in a brief demonstration that we've had here the kind of thing you can do with inFlux. Although we only used the software for about 20 minutes, we still imported CAD. We set up around 250 simulations. You know, we created monitor points, regions. We looked at the results with visualization. So it's a lot to have done with CFD in just 20 minutes time. And I hope you can imagine how that would then apply to maybe projects that you're thinking about, maybe a helideck turbulence study or a risk-based gas mapping study or explosion modeling, dispersion modeling study. So actually I want to, now that we're 15 minutes away from the end of the webinar, I do want to hand the webinar back to you for your questions about anything that we've discussed so far. If you can just submit your questions on the GoToWebinar interface. Alan, do we have any questions coming in already?
Hi, Ollie. You mentioned running several simulations. Is this calculated one at a time, or can this be run in parallel?
Yeah, that's a great question. So the question is, we've got all these simulations to run. Can we run them in parallel, more than just one at a time? Yes, you can. The simulations right now are individually running in parallel. So they're using all the CPUs on my laptop to run the simulation individually. And at the moment, it's set up to run each one after the other. Now, on very large projects, like a risk-based gas mapping project with 5,000 simulations, it's still going to take too long. So you have different options of what you can do. You can, in fact, split the project up. Once you define your 5,000 simulations, you can split the project up into smaller files and then solve those files on different machines, and then pull that data back into the main project. This is going to be a subject of a later webinar where we're going to be talking about running very large projects with inFlux. So keep an eye out for that webinar, and we'll go into that process in more detail. But basically, yes. And in fact, the way that we license that distributed computing model is that we don't limit the number you can run in parallel. So you're only limited by how much computer power you have access to. We personally at Insight Numerics use cloud virtual machines for running big projects, which means that if we want to run 1,000 simulations in a day, we can easily do that just by adding a few more virtual machines and splitting the project up to use those machines, running them, and you can get an enormous amount of CFD done in a single day. Any more questions, Alan, so far?
We've had a couple come up about our future development plans. Can you address kind of what we're planning on doing with fire, and is explosion going to be anytime soon? A lot of questions on that.
Yeah, our next item on the list is fire. So you can imagine where this would sit in the current user interface. We've got ventilation simulations, dispersion simulations, and then the item below that is going to be fire simulations. And you'll set them up just like a dispersion simulation by combining your wind and your leak, and it will know that you want to run a combustion model on that. Now, in fact, that is about 95% complete. We already have a working fire model with inFlux. It has the combustion model, the radiation model, the reaction rate model, you know, everything that you would expect from a CFD combustion model. We are just finalizing some aspects of that model for release, but that will be released very shortly, the fire modeling capability. And that will also plug into all of the existing capabilities of inFlux. So we haven't covered it in detail today, but you can do risk-based analysis to get exceedance contours for gas concentration, for example. But when we release the fire capabilities, you'll be able to get exceedance contours for radiation intensity, for example, which you can then use for PFP design or any other type of application that you would need a combustion model for. The fire simulations, just because they're solving a lot more than dispersion simulations, take about 1.5 times longer than a dispersion modeling, a dispersion simulation. So you're looking at anywhere between, let's say, 10 minutes to an hour and a bit for a fire simulation. An hour and a bit would be a fire simulation on a full FPSO. I mean, it would be a very large, simulation that would take that long. But yeah, that's going to be updated soon, and everybody who uses inFlux will automatically have their software updated to include that fire simulation. We don't license these capabilities separately. They're all included in the one software package. So all of our inFlux users will be able to use the fire modeling capabilities in a few weeks. As regards explosion modeling, that's not yet on our radar. We have, of course, thought about it, but we're focused really entirely on getting the fire model working. And then if our users really want us to add an explosion modeling model to this, we certainly will. Any more, Alan?
So taking a step back to the leak you defined, can we look at toxic gases?
Yep. Yeah, you can look at toxic gases too. So if you, let's say you wanted to add a mix of, let's say, methane and hydrogen sulfide, you can define a new gas. I'll call this gas webinar gas. And let's say you can add new components to the gas. So I might have, let's say, 90% methane. Let's have some, let's say 5% ethane. And then I'll add some CO2. And then some H2S. And then I can add that multi-component gas to the project. Now, when I then create a new leak, where am I? Yeah, when I create a new leak, I can then use that gas as the leak source. And then when I add that leak to the project, when I run that leak, I'll be able to plot concentrations of the whole gas and also each component individually. And you'll also get monitor information about each component individually. The properties of the gas are also automatically calculated for you. So the molecular mass, its specific heat, conductivity, LFL, UFL, percentages, things like that are all calculated for you. The standard library uses the same library as lots of other software in our industry, the DIPPR library, with all the various properties of gases. If you have one that's not listed here, you can also add a pure gas as well as a multi-component gas. Any more questions, Alan?
Yes. If, say, we have a dispersion of a dense refrigerant, what parameters for that compound need to be included or input?
Yeah, so if you have a dense gas, I'm assuming that's what the question is for a dense gas, you can add a new pure gas with you can either have a multi-component gas like I just showed with different properties of the refrigerant, or you can create a new pure gas inputting its properties into this form. Now, if you were to model a gas, a leak like that, you would again just use that fluid as the source of that leak, and that you would see the dense gas kind of slump towards the ground and spread. So it's, it accounts for that buoyancy kind of automatically as the as a normal ideal gas. Now, if you've got a leak that's a liquid, the capabilities of inFlux for multi-component gases, multi-component liquids or fluids are slightly more basic. We do have customers that run multi-phase simulations in inFlux by kind of creating pools and evaporating pools. But again, it's something we're looking at, is to really get a proper kind of liquid spreading. And again, we have already made progress on that. So you'll get liquid spreading and evaporation in the dispersion simulation as well. Okay, I think we have a few more minutes for a couple more questions.
Hi, Ollie. Everything right now is kind of looking at a single, not time dependent sort of models. Can we include time in our simulations?
Yep. Yeah, it's a good observation. Just for the purposes of the demo, I did a steady state simulation, meaning that I'm not looking at the time dependent characteristics of the gas cloud. I'm looking at the kind of steady state gas cloud that develops over a long period of time. But you can look at transient simulations as well. I didn't show that because they take a little bit longer, probably about 50% longer than steady state. So you can do that when you're defining dispersion simulations just by selecting transients, then selecting how long you want the simulation to run for and how often you want the results to be output. Now, when you run a transient simulation, it updates the mesh at each time step. So you get a nicely refined mesh around the gas cloud as it's developing in time. You also get the transient monitor data. So you'll get, for the monitor point, for example, you'll get concentration varying with time. For the monitor region, you will get the gas cloud size varying with time, which you can then output for probabilistic gas cloud analysis. It's very easy to do transients. As I said, they take a little bit longer, but you do get that time-dependent information from the leak. Again, very simple to do with inFlux, a transient simulation. I think we have time for maybe one more question. Alan?
That's about it, Ollie. That's all we have.
Okay, great. Great. Okay, well, thank you everyone for joining the webinar today. I hope you have had a good overview of inFlux. If you would like more information about the software, you can email us at info@insightnumerics.com. If you want to email me directly, it's ohanes@insightnumerics.com. And if you're interested in downloading inFlux and Detect3D, you can do that on our website. Just go to insightnumerics.com, register on the top right to get your account. Then once we validate your account, you can download the software. So thank you all for joining. Keep an eye out for our next webinars and hope to hear from you soon. Thanks very much. Bye.